Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tear, and this is my continuing feature on the Math Lovers book. And today I'm starting a new section again. This is section 4.5 of volume 1. Chapter 4 is on complex numbers, and section 4.5 is on what's called the polar form of complex numbers. There's two common forms for representing complex numbers. The one that's most commonly used is either called rectangular form or Cartesian form. That's where you write z equals x plus iy, where x is the real part and y is the imaginary part. But there's another way to write complex numbers is z equals r e to the I theta, where r is the what's called the norm or the absolute value. X is the absolute value complex number, and theta is what's called the argument. It's the angle that the complex number makes with a positive x-axis. Anyway, let's begin. So, yeah, I think I'm just going to skip this slide. This is where I explain it in my book, and it's a little bit hard to read. But, they say picture's worth 1,000 words, actually. Put two pictures in today. Here's what it is in a nutshell. Here's the polar form of a complex number. Here they're writing it as a plus ib in rectangular form or Cartesian form. They're using a and b instead of x and y. It doesn't really matter what letters you use. A lot of people do use a and b. But that's the rectangular form. And the polar form, there's two ways you can write it. You can either write it as r times cosine phi plus I sine phi. Here they're using phi instead of theta. And it doesn't really matter what variable you name or use for the argument. I like to use theta. Here they're using phi. And it turns out this was Euler's equation, which I talked about yesterday. Cosine phi plus I sine phi turns out to be equal to e to the I phi. Pretty remarkable result, which you can prove using calculus. But another way, the probably the shortest way to write a complex number in polar form, you just write as r e to the I phi, where r, like I said, is the absolute value. It's equal to the square root of x squared plus y squared because it's just the length of the complex number. And then phi is the angle or the argument. And there's different ways you can write that. A lot of people write it as the arctangent of y over x. That's not quite true because if x and y are both negative, then, or if one of them is negative, I think if y is negative, then you have to add pi to the argument. There is another kind of arctangent. I think they sometimes people write arctangent 2, where you take into account the sine of y, but I'm not going to do that here. But anyway, yeah. So here's another slide with formulas, and just to show you again what's going on. On the left, here's a picture, and here's your complex number a plus bi. The real component's a, the imaginary component is b. Or the other way you could write is r e to the I theta, or if you like r times cosine theta plus I sine theta. Here they're not even using r e to the I theta. Usually people don't learn this in high school. You might learn this in college once you've already learned about e and you've learned some calculus. I still prefer writing as r e to the I theta, even if you don't know what that means, just because it is a more complex, packed way of writing it, and it's pretty remarkable that it's true. But yeah, so theta, there's different ways you can write theta. Here, the right theta is the arctangent of b over a. Uh, actually, I might as well go back to my slide here. I prefer writing theta as the arc sine of x over r, and is that right? Or the arc sine of y over r, I guess. Because that r is always positive, and y can be positive or negative. Actually, I don't think that works either. You have kind of have to take into account the. I mean, you have sine theta equals x over is cos y over r, and cosine theta is x over r. Those two equations together uniquely determine theta. Between 0 and 2 pi. Theta is usually defined. The argument's usually defined between being between 0 and 2 pi. It doesn't have to be, but that's just the convention. And, once you know cosine theta and sine theta, you know theta. And you can get cosine theta, like I said, that's x over r, and sine theta is y over r. So that's how you get theta. And so that's how you can go from rectangular to polar coordinates. To go from polar to rectangular, um, I think is a little bit easier. You just say x equals r cosine theta and y equals r sine theta. So those are the formulas for going back and forth between rectangular and polar coordinates. And it's used, both forms are very useful. And I think in my next video, I'm going to talk about roots, nth roots of complex numbers. Actually, this is a case where you really want to use the polar form because it turns out that you can easily solve for the nth roots of an arbitrary complex number. There's always n of them, too. And you can solve for them using the polar form a lot more easily than you can using the rectangular form in general. And anyway, that concludes my video for today on the polar form of complex numbers. So thank you for watching. Long live math, and I'll see you guys next time. Bye.